Good evening. Welcome to our masterclass, the Byju's masterclass on Class 12 board examination. And today we are here to discuss several chapters, the first few chapters of organic chemistry from, of course, chemistry. Yes. So we start with the first three chapters as in haloalkanes and haloarenes, and then we move on to alcohols, phenols, and ether, and then onto the big chapter, the one that gives a lot of people headaches, as in aldehydes, ketones, and carboxylic acids. So what are the prime concerns as far as organic chemistry is concerned? Many people try to just memorize all the reactions, and they do actually get by. People who can retain information and who can pull it out of their head, who can recall successfully, they do really well. But having said that, you don't need to lose sleep as far as organic chemistry is concerned if you pay attention to how the paper is actually set, what is expected out of you as far as the examination is concerned. Now I'll just broadly take you through the overall pattern of your examination. You have 70 marks, and then you have 3 hours to give the exam, and you have 3 sections: organic, inorganic, as well as physical. Organic along with physical happens to be one of the most important sections. Inorganic not so much in terms of purely mark allocation. So organic actually is pretty heavy handed when it comes to mark allocation. And if you look at the overall pattern, we have 5 very short answer type questions of 1 mark each, so that is 5 marks, and then 2 mark questions, you have 5 each, and 3 mark questions, there are 12 of them, that is actually 36 out of 70 marks. That belongs to the 3 mark category. And then you have the VBQ, value based question, for just the 1 question for 4 marks. So obviously this one cannot be from chapter which has less weightage, so to speak. Yes, of course they could innovate, that can happen. I'm not saying that all this is set in stone. All this could change at the drop of a hat without notice at all. But having said that, you to top it off, we have 3 5 mark questions, 1 from each inorganic, organic, and physical. And invariably the 5 mark question generally tends to come from aldehydes, ketones, and carboxylic acids. Usually that is the pattern. Now I'm not saying that this is going to be exactly how it is going to be in your exam. This could change without notice, so be prepared. But having said that, it's good to know that this is what the general examination paper looks like. Yes. So what about the first chapter, haloalkanes and haloarenes? So the weightage is usually broken down into subparts. For instance, a 5 mark question could be in the form of 5 1 mark subparts, or it could be 1 plus 2 plus 2, or or variations thereof, as in it could be 2 plus 3 and so on and so forth. Yes, it could be 1 plus 1 plus 3 as well. Yeah. So now that we have established what to expect, you don't have very long essay type questions where there is just one a very short question which actually has a weightage of 5 marks, where you don't have any clue as to how much to write. So people in their enthusiasm, they cherry pick their favorite parts, and their favorite parts, they will actually write everything that they know, even though it is just for the 1 mark, 2 mark, or 3 mark. Whereas a 5 mark question from a not so favorable chapter, not so favorite chapter, they tend to put in less effort. Now this should not be the case. So now that we have actually outlined, let us actually take a look at each chapter in a piecemeal manner. So we start with haloalkanes and haloarenes, 4 marks. Yes. So what are the important aspects of this chapter? So like I said, there could be one very short answer type question. Now if you look at this chapter, where do you propose that such a question be asked from? Which part of the chapter from? Now it could be just one reaction. Okay, it could be the use of multi halogen compounds like CCl4 or DDT, or they could ask you something about DDT and why it has been discontinued per se. Yes, so all these things. So it could be definitely memory based question, or it could be an IUPAC question. They could give you a name and ask you to draw the structure, or vice versa, as in they could give you a structure and ask its name. Now that we have that 1 mark question out of our way, what about the remaining 3 marks? What kind of questions do you get? If we go by the past few years papers, it so happens that we have the 1 mark question out of our ways. Yes, so we have the remaining 3 marks to address, and if you look at that, then usually it is one of the 12 3-mark questions, and they happen to be in the format where there are subparts. It could be 1 plus 2 or 1 plus 1 plus 1. Yes. So if it is 1 plus 1 plus 1, where could they ask questions from? If you look at this chapter, it has a lot of information, many types of reactions, some naming reactions, some properties, dipole, polar nature of haloalkanes. Of course, it happens that the dipole moment of chloromethane is slightly anomalous, and so on and so forth. So they could test you in these broad categories, or they could go for a naming reaction. And don't forget, this chapter also has something to do with stereoisomerism. For the very first time, most students who actually go by the prescribed syllabus, they encounter chirality and stereoisomerism for the very first time. And hence, this particular tricky topic often gets tested in the form of Walden inversion or inversion of configuration. So what kind of reactions do haloalkanes undergo? So from there they actually extrapolate the graph to SN1, SN2. Both these nucleophilic substitution reactions, they have a very specific format, as in how does an SN2 reaction happen? Is there or there not an inversion? And when does racemization happen? So what is the racemic mixture? They could ask you, they could give you 3 compounds, yes, and they could ask you which one undergoes the fastest SN2 reaction. And if it is an SN2, you'll have to identify which nucleophilic substitution reaction it is. What happens to the stereochemical configuration? So if it is tertiary butyl chloride and it undergoes solvolysis, in that case it is going to be racemized. You get a racemic mixture, yes. Of course, tertiary butyl chloride doesn't have any stereochemical information, but you do get a tertiary compound which has enough stereochemical features. For instance, it has a hydrogen, or sorry, it has a methyl ethylene, some other alkyl group, and that tertiary carbon is attached to iodine, and that compound undergoes solvolysis. So what happens? So all these simple things in that you should be able to glean the information from what is given. Ultimately, you are only writing a 1-mark question, 2-mark question, or at the most 3-mark questions in a very rare case, where you have a single block and you have to write some descriptive information about that particular concept or block for 3 marks. So invariably, you end up answering a 1-mark question or 2-mark question. So you should have an idea as to how much to write. So if they are looking for a reaction, then just write the reaction out with whatever names that you can give, and whatever stereochemical data or configuration. So if there is an inversion, say so very specifically that this happens via an SN2 mechanism, via an inversion. If it is racemization, mention that the product is actually racemic. So under the product, you do mention very specifically and explicitly that it is actually a racemic mixture. So try to provide as much information as possible without actually going into writing elaborate stories. So this chapter happens to be very scoring, but if you look at the overall organic landscape, this particular chapter is where you get some memory based questions. Usually you get questions which test some fundamentals, some aspect of chemistry, rather than just recalling some obscure fact. But this chapter happens to be of the mold where people do ask some very outright obscure facts. For the matter, how DDT is manufactured, where is it used, or was it used, is it still being used, what are the side effects, is it biodegradable, and so on and so forth. What happens to chloroform on when it is oxidized in the presence of light, when it undergoes photolytical oxidation, so you get actually phosgene. Now chloroform, what kind of effect it has on the human nervous system, and phosgene, its toxicity, all these things could actually be tested in a 1-mark question. You just have a reaction and then you just write one sentence saying that phosgene is very toxic. Yes. So all these little things in a reaction, in a property, all these things could definitely be tested as far as this chapter is concerned. Like I said, you have SN1, SN2 and other beta elimination reactions like E1, E2, and what kind of products undergo beta elimination, what kind of product do you get, as in is it a Zaitsev product or is it actually a Hoffman product. So depending on the bulkiness of the base, depending on the conditions, so that has to be decided as well. So that happens to be the repertoire, that happens to be the range as far as this particular chapter is concerned. Also, there is one very peculiar aspect of electrophilic as well as nucleophilic aromatic substitutions. Yes, so you have haloarenes. How haloarenes are synthesized? So what is the function of an alkyl chloride in a Friedel-Crafts reaction? Friedel-Crafts alkylation, Friedel-Crafts acylation, if you use an acyl chloride, and so on and so forth. What kinds of catalysts are being used? Are they truly catalytic, and so on and so forth? That is also very important. So how to synthesize haloarenes, that also happens to play a very important role. Last but not least, there is one very specific reaction where you are given chlorobenzene and that gets converted to phenol. So I am very specifically referring to nucleophilic aromatic substitution reaction. So it is actually a nucleophilic substitution, but it happens over the benzene ring as an aromatic species. So how does that happen? What are the conditions, and so on and so forth? So this chapter beautifully makes a transition from haloalkanes, haloarenes, and then just like that we actually are talking about phenol, which once again happens to be the chapter of interest as far as the next major chapter in organic chemistry is concerned. So the next chapter is going to be alcohols, phenols, and ethers. So before that, I'll just broadly outline some naming reactions from haloalkanes and haloarenes. You have Sandmeyer reaction. Sandmeyer reaction has some connection here from amines as far as bringing out haloarenes, synthesis of haloarenes. Yes. So iodobenzene, chlorobenzene, fluorobenzene, bromobenzene, how do you synthesize? So all those things. Can you put a cyano group? So this chapter does have some intersection with amines, which of course we'll discuss in a later episode. So what are the other naming reactions? You have Woods reaction, you have Schwarz reaction, you have Finkelstein reaction. So these are Schwarz and Finkelstein happen to be halogen exchange reactions. Yes. So you should know about the solubility of NaCl, NaBr in acetone. What drives these reactions forward? How do you synthesize an alkyl fluoride? In your textbook, you might find some data as to what kind of nucleophiles react with alkyl halides and what kind of products are formed. So you could actually get nitroalkanes or bidentate nucleophiles. You have CN-, you have NO2. So all these things could actually, depending on if it is AgNO2 or KNO2, you get different products. So what kind of products you get, all these things could be tested. So those are actually memory based. But there are some conceptual topics like stereochemistry, and then there are some other naming reactions like Woods reaction, Fittig, Woods Fittig, and their variants. So there we actually wrap up haloalkanes and haloarenes, and then quickly move on to alcohols. Now alcohols, once again you have 4 marks, but this chapter as such, if you look at alcohols, phenols, and ethers as a separate topic, then you don't actually get that many questions. Now that happens for a very important reason, because this is bang in the middle of organic chemistry. On one side you have hydrocarbons and haloalkanes, and on the other side you have the heavyweights, aldehydes, ketones, and carboxylic acids. And alcohols invariably they tend to be intermediates if you want to convert those to these or these to the former. So in that respect, alcohols, since they are very important intermediates, invariably you will find a lot of questions which are based on conversions. So practice as many conversions as possible. Now try not to memorize them, but have a broad outlook as to how to convert such and such compound to such and such compound. This comes with practice, and of course there could be several ways of accomplishing the same conversion, but you just have to practice and soldier on, because as a good rule of thumb, if you complete all the conversions which have been asked in the previous years, and if you are good to go with the conversions in your textbook, that actually holds you in very good stead. That puts you in a very, very wonderful position, so to speak. So what other things are important? Chemical tests involving alcohols. So how do you distinguish primary, secondary, and tertiary alcohols? The Lucas test, where is a Lucas test successful, where it isn't? So if you have the carbon chain with more than 6 carbons, is it applicable, and so on and so forth. So these things are very important. And once again, 2-butanol is actually, it has some stereochemistry involved in it. So if you look at the carbon of interest, carbon number 2, it is attached to 4 different groups. So bring your fundamentals from stereochemistry to this place as well. In saying that, alcohols undergo a variety of reactions. So the OH group of ROH is not a good leaving group. How do you make it into a fantastic leaving group? all these things happen to be really, really important. Don't forget Grignard and the Grignard synthesis from haloalkanes until carboxylic acids and even further. Grignard synthesis very, very, very important. It is in fact one of the Nobel Prize reactions as well. So it's very important. And if you look at this particular chapter, different methods to synthesize phenol, that becomes very important. And how do you distinguish between alkyl alcohols, as in straight chain alcohols, and phenol? The reaction of phenols, the acidity of phenols, compare and contrast it with alkyl alcohols, primary, secondary, tertiary, and so forth. The reactions of alcohols with phosphorus halides, that also happens to be very, very important. How do you make the OH group into a good leaving group? If you get an alkali metal to react with the alcohol, what happens? Then it becomes RO minus, and that actually becomes a very tough nucleophile. If you actually contrast it with a neutral ROH alcohol, that is not as good a nucleophile. So alcohols can act as nucleophiles as well as electrophiles, depending on what happens with them. Yes, so the characteristic reactions of phenols, very important reactions. If you look at the naming reactions, then you have a Reimer-Tiemann, then you have Kolbe synthesis, Kolbe's reaction, then you have synthesis of aspirin, oxidation of phenol to benzoquinone, and the likes. And also pay attention to some obscure facts like you have enzymes, so enzyme catalyzed reactions as well. So what happens, how do you synthesize ethanol, methanol, what are their industrial applications, uses, zymase, invertase, where they are applied, and so on and so forth. So you get 2 questions of 2 marks each, so keep that in mind. Once again, this chapter may not be it may not be set in stone that you get exactly only concepts involving alcohols or phenols. Don't forget there is a small matter of ethers, application of ethers, and especially hydrolysis. So you have an ether, it could be symmetrical, unsymmetrical. You have a Williamson synthesis and hydrolysis of ethers using a Lewis acid like BF3 or HI, and of course invariably you will use heat in that process. So what kind of hydrolysis happens, and especially if it is a phenyl ether, what happens if it is a methyl phenyl ether and it undergoes hydrolysis with HI, so what happens? So all these things you need to pay attention. And how do you distinguish chemically ethanol and phenol? That also happens to be a very important test. I'm very specifically talking about ferric chloride test. Yes, so that's that, and we come to the big weapons of organic chemistry in aldehydes, ketones, and carboxylic acids. So this chapter alone actually fetches you 6 marks. So overall, just the 3 chapters, haloalkanes, alcohols, phenols, ethers, and this chapter, if you look at it, it's going to fetch you 4 plus 4 plus 6, and that is what, 14 out of 70. That is 20% of your entire marks. So combine that with your practicals, and you are actually acing chemistry. Maybe not so much acing, but yes, you are actually safely across if you know what you're doing. If you can just balance out a few things from other chapters, yes, you are very safe. Having said that, what are the most important things? Now this chapter happens a lot of naming reactions, a lot. Definitely the most important of them being haloform reaction. Now a lot of people would say it's actually aldol, but if you look at the number of questions that get asked either from the board exam or even from competitive exams, I don't know, a lot of people generally favor haloform reactions a lot, quite a lot actually. And they ask you to distinguish between 2 aldehydes, and one of them would actually give you a positive haloform test, one of them won't, and so on and so forth. So how do you chemically distinguish different species from this chapter? Very specifically aldehydes and ketones, a mixture of aldehydes or an aldehyde and a ketone, or a ketone and a ketone. That is very important. The next most important reaction, of course, is it has to do with alpha hydrogen. When I say alpha hydrogen, it is definitely going to, of course, include aldol, the aldol product, and then its dehydrated elimination product if it is base catalyzed, or even catalyzed alpha beta unsaturated carbonyl compound if it is going to be acid catalyzed. Yes, so you need to know the specifics. You need to be able to write one example. You need to be write in 2 lines what is an aldol reaction, or when I mentioned the presence of alpha hydrogens, the absence of them, of course, is going to give you possibility for the Cannizzaro reaction, like that. So there are several different naming reactions in this chapter. All these are very, very, very important. So when I speak of aldol, since it has been done to death, it has been asked so many times, they might actually feel a little bored and slightly up the level. as in they might ask you what is give an example of intramolecular aldol condensation or cross aldol condensation. So in that respect, you should be able to actually bring about one example of each, and talk in very brief, as in you need to be able to write a couple of lines as to exactly what is happening. Yes, so gone are the days when they ask you what is an aldol condensation, give an example. No, so they'll actually ask very directly, give this reaction, what happens here, and then they will ask you, since there are many subparts, they try to go for breadth. So that is the point I'm driving here. Yes, so all naming reactions, and as a cardinal rule of organic chemistry, you have to practice a lot of conversions. It's a must. And all the different chemical tests. So what happens with the bisulfite addition, what happens with the HCN addition, cyanohydrin formation, what happens with 2,4-DNP, what kind of precipitate do you get. Yes, all these things become really crucial. So 2,4-DNP is just one subset of imine formation, so that is also very important. And there is this broad category of reduction reactions. Yes, how alcohols get oxidized to either aldehydes, ketones, or carboxylic acids, how different compounds, when I say different compounds, it could be a carboxylic acid, could be an alkyl nitrile, and it could be an alcohol, different compounds, it could be an ester. So where does diol H come from? What happens to tritertiary butoxy aluminum hydride? So different hydride donors, hydride reducing agents like lithium borohydride, sodium borohydride, lithium aluminum hydride, and the likes, what do they do? All these reduction reactions, very specifically, if I have to put out three names, then it is going to be the Clemmensen reduction. It happens under vigorous conditions using zinc amalgam HCl, acidic medium, and there is the base version of such reduction, which happens to be Wolff-Kishner reduction, where you have hydrogen and KOH or some base, and of course invariably heat is actually involved. Yes, so how do you convert a carbonyl into a hydrocarbon? If you can do the reverse, that also helps. And another important naming reaction happens to be the Rosenman reduction. What is the Rosenman catalyst, and so on and so forth. There are some mentions of some comparison as to Rosenman catalyst and Lindlar's catalyst, but let us not go there. It is slightly out of syllabus, but I think I've broadly outlined some important topics. Are there any more? Have we left out any important naming reactions? Yes. If you look at carboxylic acids, then we are definitely leaving out Hell-Volhard-Zielinski. So you have a carboxylic acid, it is treated with phosphorus and some halogen. Phosphorus trihalide in situ is prepared, and there is a halogen exchange reaction happening between RCOOH and RCOX, and you get alpha halogenated acid as a product. So that's the gist of Hell-Volhard-Zielinski reaction. There is also Fischer ester synthesis, different methods of synthesizing esters. It happens to be an equilibrium reaction, and how do you drive the reaction forward or backward, what is the solvent, and so on and so forth. That also happens to be very important. Having said that, since there are too many reactions, don't forget some obscure reactions like Etard reaction, Stephen aldehyde synthesis. Yes, how to interconvert between any of the carboxylic acid derivatives. So conversions become of paramount importance as far as this particular topic is concerned. And then carboxylic acids are in fact acids. Yes, very simple. Yes, so if they are acids, what are their acidic strengths, and how the acidity is affected as far as the substituents present on an alkyl chain, or it could be even para-nitrobenzoic acid. What happens? Is the acidity increased? Is it lessened? Why? And so on and so forth. So such questions can also be asked. Don't forget, although it is for 6 marks, invariably it happens to be 1 plus 5, and the 5 is not just one big log of a long elaborate question. It has subparts and they go for depth. So definitely it pays to focus on depth, to be able to recollect examples and practice conversions, and very specifically find out what chemical test to employ to be able to distinguish between what kind of compounds which are given. Yes, that is very important. Also reactions of carboxylic acids with some bases, sodium bicarbonate, NaOH, ammonia. So how do you prepare an amide, properties of amide, why amides have abnormal melting points, boiling points, abnormal boiling points, and the formation of dimers that has an intersection with physical chemistry as far as carboxylic acids are concerned. Yes, so from the chapter solutions. So all these things happen to be really important. Last but not least, I think I might have left out the reaction of a carboxylic acid with phosphorus halides. So likewise, you also have acid chlorides, acid anhydrides, and the likes. So what happens when aniline is made to react with an acid chloride, phenol is made to react with an acid chloride, and alcohol is made to react with an acid chloride, and the likes. So how different, how do you convert from one form of carboxylic acid compound into its derivative, and vice versa. So all these things, they become very important. I think I've just broadly outlined just about everything. Now if there are some questions, that would be wonderful. So we have some questions. So what is SNAR mechanism? So SNAR mechanism is nothing but, I actually mentioned this as part of haloalkanes and haloarenes. So you have chlorobenzene, and chlorobenzene, how do you actually convert it into phenol? So you have NaOH, concentrated NaOH, high temperature, because if you look at the intermediate of this reaction, then it of course has to lose aromaticity and then gain it back, and it has to be a nucleophilic substitution, as in OH minus will attack that particular sp2 carbon which is attached to chlorine, and aromaticity is lost and it is regained back with the expulsion of chlorine. Now this would be accentuated, it would be facilitated or made more easy by something which is very strongly electron withdrawing, say a cyano group, or very specifically a nitro group. So you have chlorobenzene. If you compare it with orthonitro-chlorobenzene, the latter would actually undergo SNAR much faster. So if you put another, if it is orthopara-dinitro-chlorobenzene, then that would undergo much, the same reaction with much more ease, so to speak, and at a lower temperature. And you can just extrapolate the whole thing from there. Now, I'm not able to look at the questions. Let me just get back. So, hold on. Invariably, I see that what kind of questions you get from aldehydes and ketones. What kind of chemical tests? So they would actually give you a compound which happens to be a little tricky. As in, they will ask you to distinguish between, say, benzophenone and acetophenone. Now, in such case, if you look at one carbonyl compound, this happens to have the CH3CO configuration, which is very conducive for haloform reaction. So if you subject that substrate to haloform reaction, that would actually give you the yellow precipitate, and thus confirm that it is in fact conducive to haloform reaction. Whereas the other one, where the carbonyl is surrounded by two phenyl groups, now that is not actually going to undergo this kind of reaction, is it? Now this kind of reaction will also be given by compounds which have a secondary carbonyl carbon, yes, which is attached to a methyl group. So there is a carbon, it is attached to OH group, methyl group on one side, and there is something else on the other side. Now that would also actually undergo this reaction. So I2 and NaOH, or NaOI, or lead tetraacetate, any strong oxidizing agent, that is going to give the same kind of reaction. So the next question is, how to form benzene from methyl trichloride? Methyl trichloride, how do you form benzene? I don't think you can actually form benzene from methyl trichloride. How do you form that? You can't do that. Now, there might be some obscure reaction, but if you actually look at good yields, when we want to conduct a very specific chemical reaction, now it is actually going to give you a very proper, yield of a reaction. So we have some input costs and we need to optimize for a good yield of the product. So why would you use chloroform to synthesize benzene? There are much better methods. Please tell some exceptional reaction from organic chemistry. My vote definitely goes to Hell-Walhart-Zelinsky reaction. It's a very interesting reaction. You have RCOOH, and it is made to react. It definitely has an alpha hydrogen, and this is made to react with phosphorus and it could be iodine, phosphorus bromine, phosphorus chlorine in situ, and you actually get alpha halogenated reaction. Yes, and About carboxylic acids, I think I've elaborated that really enough. So I think we have actually come to the end of this session. Hope you had fun. Looking forward to see you next time with the remaining chapters.